What does view do in PyTorch? What does .view do to a tensor x? What do negative values mean?
View reshapes the tensor without copying memory, similar to NumPy's reshape. Given a tensor A with 16 elements. To reshape this tensor to make it a 4x4 tensor, use. Now it will be a 4x4 tensor. Note that after the reshape the total number of elements need to remain the same. Reshaping the tensor A to a 3x5 tensor would not be appropriate. What is the meaning of parameter -1? If there is any situation that you don't know how many rows you want but are sure of the number of columns, then you can specify this with a -1. Note that you can extend this to tensors with more dimensions. Only one of the axis value can be -1. This is a way of telling the library, give me a tensor that has these many columns and you compute the appropriate number of rows that is necessary to make this happen. This can be seen in this modeled definition code. After the line x equals self.poolf.relu self.con2x, in the forward function, you will have a 16 depth feature map. You have to flatten this to give it to the fully connected layer. So you tell PyTorch to reshape the tensor you obtain to have specific number of columns and tell it to decide the number of rows by itself.
Let's do some examples, from simpler to more difficult. The view method returns a tensor with the same data as the self tensor, which means that the returned tensor has the same number of elements, but with a different shape. For example, assuming that -1 is not one of the parameters, when you multiply them together, the result must be equal to the number of elements in the tensor. If you do a .view 3, it will raise a runtime error because shape 3x3 is invalid for input with 16 elements. In other words, 3x3 does not equal 16 but 9. You can use -1 as one of the parameters that you pass to the function, but only once. All that happens is that the method will do the math for you on how to fill that dimension. For example, a .view 2 -1 4 is equivalent to a .view 2 4 16. 2 by 4 equals 2. Notice that the returned tensor shares the same data. If you make a change in the view, you are changing the original tensor's data. Now, for a more complex use case. The documentation says that each new view dimension must either be a subspace of an original dimension, or only span D plus 1, D plus k that satisfy the following contiguity-like condition that for all I equals 0, k, 1, stride I equals stride I plus 1, x size I plus 1. Otherwise, contiguous needs to be called before the tensor can be viewed. For example, notice that for a_t, stride 0, not equal stride 1, x size 1, since 24 not equal 2 by 3.
View reshapes a tensor by stretching or squeezing its elements into the shape you specify. How does view work? First, let's look at what a tensor is under the hood. Here you see PyTorch makes a tensor by converting an underlying block of contiguous memory into a matrix-like object by adding a shape and stride attribute. Shape states how long each dimension is. Stride states how many steps you need to take in memory till you reach the next element in each dimension. View dim1, dim2 returns a view of the same underlying information, but reshaped to a tensor of shape dim1x dim2x by modifying the shape and stride attributes. Note this implicitly assumes that the new and old dimensions have the same product, i.e. the old and new tensor have the same volume. PyTorch -1. -1 is a PyTorch alias for infer this dimension given the others have all been specified, i.e. the quotient of the original product by the new product. It is a convention taken from numpy.reshape. Hence t1.view3, 2 in our example would be equivalent to t1.view3, -1, or t1.view1, 2.
Torch.tensor.view. Simply put, torch.tensor.view, which is inspired by numpy.array.reshape or numpy.reshape, creates a new view of the tensor, as long as the new shape is compatible with the shape of the original tensor. Let's understand this in detail using a concrete example. Another thing to observe is that we used a -1 in one of the places in each of the shape tuples. By using a -1, we are being lazy in doing the computation ourselves and rather delegate the task to PyTorch to do calculation of that value for the shape when it creates the new view. One important thing to note is that we can only use a single -1 in the shape tuple. The remaining values should be explicitly supplied by us. Else PyTorch will complain by throwing a runtime error. Runtime error: only one dimension can be inferred. So, with all of the above mentioned shapes, PyTorch will always return a new view of the original tensor T. This basically means that it just changes the stride information of the tensor for each of the new views that are requested. Below are some examples illustrating how the strides of the tensors are changed with each new view. Now, we will see the strides for the new views. So that's the magic of the view function. It just changes the strides of the original tensor for each of the new views, as long as the shape of the new view is compatible with the original shape. Another interesting thing one might observe from the strides tuples is that the value of the element in the 0th position is equal to the value of the element in the 1st position of the shape tuple. This is because the stride 6, 1 says that to go from one element to the next element along the 0th dimension, we have to jump or take 6 steps. i.e. to go from 0 to 6, one has to take 6 steps, but to go from one element to the next element in the 1st dimension, we just need only one step, for example to go from 2 to 3. Thus, the strides information is at the heart of how the elements are accessed from memory for performing the computation. torch.reshape. This function would return a view and is exactly the same as using torch.tensor.view as long as the new shape is compatible with the shape of the original tensor. Otherwise, it will return a copy. However, the notes of torch.reshape warns that contiguous inputs and inputs with compatible strides can be reshaped without copying, but one should not depend on the copying versus viewing behavior.
If you want to see more, please consider subscribing.